Hope everyone slept well. I find that something about knowing that there's deep, fluffy snow outside, somehow it translates into a deep, fluffy bed and a feeling that you're safe and surrounded and comfortable and therefore able to get a good night's sleep. So I'm very happy to hear that. From talking with everybody, we had an absolutely fantastic day yesterday, and I'm just absolutely thrilled with the quality of the presentations, which were superb, as well as the quality of the interaction, which was better than I could have expected. So it was really exceeded my expectations in every way for all of the discussions that occurred yesterday. And I'm very happy knowing that these discussions and the presentations will be streaming from the conference website for the whole next year, and knowing that many, many hundreds and thousands of other people will be able to benefit from the hard work that all of you put into the presentations and for the very interesting dialogue that occurred in between. Today promises to be just as exciting as yesterday. We've got a keynote speaker today in Professor Warwick, who literally embodies the ideas and visions that Ray Kurzweil began to explain in his keynote address yesterday. And we have a continuation of the interplay between nanomedicine and telemedicine to, again, give us a feel for what the next decade in medicine is likely to look like. Our chairperson for today is my colleague, Baruch Blumberg, and I gave a bit of an introduction to Barry yesterday, but I will say that every time I'm in Barry's presence, I really feel that I'm in the presence of an angel. I mean, that although I know that all the work he did was, like all of us, pursuant to our own scientific curiosity, inventive nature, and ultimately love of biology. In Barry's case, those three aspects of all of our personalities were able to be combined ultimately into a vaccine against hepatitis B, which was really the first cancer vaccine, since liver cancer is a all-too-frequent sequelae of chronic HBV infection, and so prevented countless cases of liver cancer, and not to mention has prevented countless cases of chronic hepatitis, to the point that the United Nations has estimated that over 100 million lives have been saved as a consequence of Dr. Blumberg's inventions. And the other thing which is great is that while a lot of Baruch's activities originally occurred, well over 2 decades ago, he has not rested on any laurels at all, not even on his Nobel laurels, but has been relentless and indefatigable in continuing to proselytize for the importance of heightened rates of HBV vaccination, especially in developing countries, especially in Asia, where the problem is perhaps at its most severe, and has continued to use his knowledge of biology to help the government in many different ways, and even at the furthest outreaches of biology with his guidance of NASA's astrobiology program, which actually helps us understand the beginnings of biology right here on the Earth, much of which, if it's not astrobiological in nature, it's pretty weird. And so studying astrobiology helps us understand extreme biology here on the Earth, which in turn helps us understand the very beginnings of cellular processes. And it's those cellular processes that we need to understand to ultimately be successful with our nanomedical ambitions. So with those words of introduction, I'd like to turn the podium to Dr. Baruch Blumberg, who will chair today's sessions.
Thank you, Martine. I couldn't help thinking, I wish my mother could have heard you say that I was an angel. I knew that would have fulfilled her every wish for me. And I hope I can continue to live up to that. I may be getting closer. Well, what I'd like to do is just make a few comments, really, on the nature of this meeting and relying to a large extent on the papers we've already heard, the questions they've raised. One of the fundamental questions is, what's the difference between biology and engineering? The model for biology, particularly in medical biology, has been a kind of a mechanical engineering based on physics kind of model, but it doesn't entirely fit. If that were the case, we could have followed by now Victor Frankenstein's example of having put together all the bits, and in his case, putting a little bit of electricity through it and creating a living organism of some sort. Now, there's a whole field of synthetic biology, but I think it's fair to say that this has not yet been accomplished and conceivably may be out of reach. Dr. Sklabasi, in his talk yesterday in the morning, spoke about sloppy logic of the brain. And in a way, we can constitute much of biology is, to use that term, sloppy, is perhaps a little extreme, but it's certainly not as it's not as ordered as the as we expect biology to be. Physics or engineering to be. Now, I think part of the reason, and I talked to Ray Kurzweil about this briefly yesterday, is the nature of our genome. Whereas in engineering, you try to get sort of maximum efficiency out of the device that you're making. When you're making a bridge, you want it as safe as it can be and carry as high a load and still fit in pretty exact specifications. But for biology, you have to deal with the genome, the human genome, the case that mostly we're interested in now. But the genome is not designed for perfection. It's designed for getting by. First of all, we have we carry our history inside us. Many of the genes are highly conserved. It's amazing how much conservation is, and how much of our preceding species are incorporated in our own genome. I think a mind-boggling result of 20th century science was to discover that archaea share a third of their genome with humans, with mammals. And that's really quite remarkable. So what it means, or interpretation of that, is that the genome is, nature sort of doesn't like to make a lot of new genes, and it's quite happy to retain the old ones and do the best it can with it, you might say. Now, also, we need a lot of currently not usable genes, currently not optimal genes in our genome. And as you know, only about 7% of the genome produces proteins. And they're made to have a huge importance, of course, but having to do with regulation and so forth. And there are actually more viral genomes, sequences that are homologous with viruses in our genome than there are reading frames that make proteins. So we have a lot of extra stuff there. But it's not useless by any means, because those are the genes that are available to start being used, in a sense, to express themselves when the environment changes. And we're talking about an unknown future change in the environment, and an unknowable one. I mean, no one can predict exactly what the environment's going to be like. So one of the great mysteries of evolution is that the genetic model of evolution, is that there are genes available which can be called upon for future use. So in effect, you can say that anything that's perfect is by definition not perfect, because it's not prepared to deal with this unknown future. So I think that is when I presented this to Ray, he said, "Well, machinery is sort of like that," but nevertheless, I think there's a qualitative difference that we have to kind of take into account. And sadly, much of that depends, it's not sadly, as all scientists know, particularly in biology, well, in any science, depends on a kind of intuition in which you have a sort of feeling about how the biology is going to work. I'm just reading the history of quantum physics, and it's quite amazing how quantum physicists very often, based on some picture they get in their mind, which they then decide is how the nucleus of the atom looks, and then go on to develop the mathematics for it. Now, another interesting aspect that we deal with is how do machines differ from humans? In other words, what does it mean? What does it mean to be human? Now, you recall that question was brought forward very dramatically, and I think that impressed most people, and that is the character of Hal in 2001, A Space Odyssey. To begin with, it was the only character in the movie who had any personality. The rest were fairly, occasion-driven. They didn't seem to have any great depth, whereas Hal did, including a profound memory. But we don't have a Hal, and what is it that makes humans different? Well, I think one of the great differences is the need to explore. Now, this issue about the difference between humans and robots and machines is very important in NASA, because decisions have to be made about whether you have human missions or robotic missions. Human missions are infinitely more expensive. The engineering is much more difficult. You have to have life-preserving capability. And the question is, what is it that humans import? Well, the major reason for having human missions is this basic need to explore. I think there are other reasons why it's advantageous. But that's the major reason. People have to explore. And in effect, NASA recognizes this need in the public. And that's why when NASA has human missions that tend to be a great deal more public support, then even though these robotic missions are mind-boggling, they don't attract people as much. So can you program a machine, a device, a computer, or a robot to see something that nobody's ever seen before? Can you develop a kind of pattern that is inherent in humans to understand the new, to appreciate when something is different than anything they've ever seen before? A large part of that is, I think, due to the incredible complexity of the brain, and we've heard about that today, and with this concept of implanting a computer to have some effect on behavior, essentially, in the brain, well, in repairing defects in the brain, and the medical goals that are sought for nanobiology. So can a computer or machine discover something that's never been seen before? When President Kennedy launched what became Johnson Space Center, he talked about entering this new ocean, which I believe was a quote from Columbus. And that was the sense. We were off to see things that nobody had ever seen or measured or sensed before, and can a machine do that? Humans have discrimination and pattern recognition. Now, there's a couple of things. Can you define things that people do and machines can't? Well, I'll give you a few what you might call homely examples. And one of them is Galaxy Zoo. Some of you may be familiar with this. The millions of new galaxies have been seen. And it's very important to kind of characterize their shapes. That is, whether they're elliptical, whether they're spiral, which way the spiral goes, how many arms there are in the spiral, whether there are new things that nobody's ever seen when you start looking at them. Well, there's 10 million. There's an automatic satellite camera. It's an Earth-based telescope with camera that's automatically scanning the sky and looking for galaxies. Well, nobody's ever seen those galaxies, actually. It's an autonomous device, and it gets stored in its memory in digital form. Well, if you wanted to have professional astronomers look at that, they estimated it would take like several hundred years to look at all these millions and millions of galaxies. That's only the ones that have been identified so far. But what they've done is they've enlisted 80,000 volunteers who look at the images, and then they get a tutorial over the net, and they're meant to classify them. Then they have internal safeguards on accuracy, and they get a kind of vote of, let's say, 20, 30 people have to look at it and concur. And they then can classify it, and it's a fairly simple classification. Well, that's given an awful lot of information. And they decided, after some attempt, to develop a scanning method using, and that didn't really work very well. So they've got these 80,000 enthusiastic volunteers. They're now on to Galaxy Zoo number 2, and they're starting number 3, which they're going to be verifying. They want to get it to a point where it'll be accepted by the scientific community. That's one example. The other thing is that prior to the Apollo mission, there were 5 orbital missions to take photographs of the moon. They photographed about 90% of the moon, and to select a landing site. Well, that landing site was selected. That was the mission. That's what you had to do, and that's the end of the money to fund that stuff. So those images are still around, and for the most part are unanalyzed. In fact, they were lost. Nobody knew what quite happened to them, and they reappeared on eBay. And the tapes, the download from these the analog images, and they're now at a location on NASA Ames Research Center under the supervision of the NASA Lunar Science Institute. And they also found the reader, those reel-to-reel things they used to see in all of science fiction movies. They were lost, and they found one in somebody's garage. And they found a highly competent technician in Alabama who knows how to deal with it. So all these things are now housed in what used to be a McDonald's restaurant, and the project is referred to as the McMoon Project, locally, not nationally. But in any case, so the point is we'd like to analyze those, among other things, to find out the flux of new impacts on the moon. And they had some seismographic, they were able to triangulate the moon. With seismograph, they've identified the highly likely location of several would have been fairly major impacts. Again, this is most easily done by humans. So there's something about that characteristic about making patterns that is human, and the challenge really is to see if that can be duplicated, or if it can be duplicated, do you want to? Now I'm going to end up with a bunch of images. I think another human characteristic, we're often stimulated by things that we see or sense in some way, scenes in nature and so forth, and it kind of it gets the imagination rolling. So I'm going to show about 8 or 9 pictures, 10 pictures, and then so there'll be the picture first, and then there'll be a legend for the picture that follows. So we can show the first one, which The following ones are better. This is a image between those green lines. You'll see a faint white line, and let me see, the pointer.
Is the red
Right.
laser symbol.
There's this faint white line in here between the green lines. Okay, that's a radio astronomy image, a digital effect, and that is Pioneer, let me see, 10. I'm sorry, it was Voyager. It was Voyager.
Okay,
not Pioneer.
Voyager 1,
Okay.
yeah.
It was Voyager 1, and you can see the two peaks over there are the radio images. And this is done on this new array that's in Medicine Hat, California, near in the Cascades, or in the valley near the Cascades. So that was that's a message from something that's left, 20, 30 years ago, and way on the verges of of our planetary system. Now, this is a polar view of the North Pole area. And you can see Greenland over here, and this is the Canadian Arctic archipelago, which is more or less due north of us, but way due north. And this is the Northwest Passage going through here. And it's open in the summer. Now, this is the first time that that's been seen in, I think, in a long time, or perhaps ever. And this is an image of Mercury. As you know, we have a satellite has gotten to, after about 4 or 5 years, it reached Mercury. It did a flyby and took these amazing photographs, and it's now, in a year or two, is going to be doing an orbital mission. And this is an image of the sun showing these big sunbursts in I think it's infrared image of it, which helps in understanding sun weather. And this is an amazing picture of a galaxy with those bright spots being areas of star formation. And this is a rather strange geological formation in Siberia, which is not an impact crater or a volcano, and it's a great help in geological exploration, having images of this nature. And this is the snow, water ice that was scraped up on the recent Mars lander that went to just the edge of the South Pole. And this detection of snow ice was the first direct evidence for that had been sensed spectroscopically. And this again, another image of the sun showing a magnetic discontinuity in that fantastic shape. And a beautiful image in this color. And again, that's the nasty hurricane that kind of lingered over Cuba and Florida for a long time, causing a great deal of destruction. But again, a remarkable image. And that is one of the moons of Saturn. They have, the recent Cassini flybys have revealed some interesting relations between the moons and the rings around Saturn. Now, and this, including the area in now, is the aurora image from space in a mosaic image. And another fantastic galaxy. Well, we can have the computer off now, these slides off now. Well, I leave you with that. It took too much time, but we're looking forward to our speakers this morning.